In this video, we'll be looking at how we can solve differential equations of the form y prime plus a of xy is equal to 0. Now, this type of differential equation has a name. It's called a first-order homogeneous linear differential equation. And obviously, I used a lot of barbaric words here. But first order basically means that the highest order of the derivative, the highest degree of the derivative is 1. And therefore, we have at maximum a first derivative. It's not a second derivative. It can be at most a first derivative, which is what we have here, y prime. Homogeneous, in the case of first order linear differential equations, means that we have a 0 here essentially. And then we only have expressions that depend on y. But you will see that the terms homogeneous and linear have its importance when we are dealing with more complicated differential equations. So I don't think it's wise to spend time on the definition of these terms now. Now, the first thing you need to do when you have this type of equation is change the prime notation with the d by dx notation. In other words, we have dy by dx plus a of x y is equal to 0. So notice that I've just changed the prime with the d by dx. And the reason we do that is to better understand how we will use integration later on. Now the second thing we need to do is separate the y-dependent variables with the x-dependent variables. So here we want to separate the a of x from the y's. So we bring the axy on the other side. So we essentially subtract by a of xy. And now, as I said, I want to bring y to where we have a dy, essentially. And therefore, we have a 1 over y dy dx, which is equal to minus a of x. And now, here's the trick. You separate the dx from the dy. And the way you do that is by multiplying by dx. Now, of course, there are several problems here. First of all, the y must not be equal to 0. Okay, so we have a problem if y is equal to 0. But as we can see, if y was equal to 0, it would be a trivial solution to this differential equation. Indeed, we would have y prime, which would be 0, plus a of x times 0, which is equal to 0. So y is equal to 0 is a trivial solution. So we're not interested in that, and therefore we can divide by y. And now we have that if we multiply by the dx, we have 1 over y dy is equal to negative a of x dx. And now what we can do is integrate on both sides. And so the reason why I changed the prime notation with the dy dx is to understand what variables we will be integrating here. And one crucial element to note is that we can perfectly separate the dx and the dy's here. Loosely speaking, you have to see the dy's and the dx's as little increments. And basically what we were saying is that 1 over y times a little increment, a little change in y, is equal to negative a of x times a little change in x. And I want to reiterate, the reason we do this is to further understand with respect to which variable we integrate on either side of the equation. So let me show you what I mean. So now we can integrate on both sides. But on the left-hand side, we integrate with respect to y, because here we have a dy and not a dx. And similarly, we was here on the right-hand side, we integrate with respect to dx. So essentially, we have turned a problem of differentials into a problem of integration. So instead of having a derivative, we have an integral, and we know they're closely associated. And this makes sense why we have a problem of integrals, because here we have a differential equation. And what does this mean? It means that we have an equation with derivatives and we are trying to find the function y. So since we already know something about y prime, we are trying to lower the degree, so lower the order of the derivative all the way to y. And the way we do that is through integration. Now the integral of 1 over y dy is ln of the absolute value of y. And this absolute value is important to remember, as you will see later on, is equal to the antiderivative of a of x. And we will call that capital A of x. So we have negative capital A of x. Essentially what I've done here is said that the antiderivative of a of x is capital A of x. And so the indefinite integral of negative a of x dx is negative capital A of x. And of course, we can't forget about the constant. So let me write that down. Since capital A of x is the antiderivative, the derivative of capital A of x is lowercase x, or a prime of x is equal to a of x. And so taking the exponential on both sides, we have that the absolute value of y is equal to e to the minus capital A of x plus times, or we add into the exponential c. And so the absolute value of y is e to the c times e to the minus a of capital A of x, where we have used the exponential property. Now c can be any real number, of course. And furthermore, this means that e to the c is also a constant, but it's a positive constant. And that's what we have to remember. So we can call e to the c a positive constant, so I'll denote it with the r plus notation. But now what we have to notice is that we have the absolute value of y. So now we have that y is equal to the constant k e to the minus a of x, capital A of x. And let me explain what I've just done here. So we have that the absolute value of y is e to the c times a to the negative capital A of x. Well, the absolute value always spits out a positive number. And we want just y, not the absolute value of y. And so y can be either a positive or negative number. And the sign of y is exclusively determined by the sign of this constant k, because e to the minus capital A of x is always a positive number. And so k can either be a positive or negative number. What's even more interesting is that k is actually a real number. So it can be negative, positive, but also equal to 0. And why can it be equal to 0? Well, here we divided by y. But if you remember what I said, a solution to this differential equation can be y is equal to 0. Indeed, y prime will be equal to 0 in that case, and y will be equal to 0. So it satisfies this differential equation. So in this case, we suppose that y is different than 0 in order to divide by y. But y can also be equal to 0. And that is why k, in this case, is a real number. Because even if k is 0, well, y is equal to 0 is actually a solution to the differential equation. And to quickly sum up, when we're trying to find solutions for differential equations, we're trying to find functions that solve that differential equation. We're not trying to find the value for a variable x. We're trying to find a function y, which is a function of x. So y can be written as y of x. And in order to solve differential equations, we have to turn the problem of differentiation into a problem of integration. And the way we did that in this video is by separating the differentials in terms of y and the differential in terms of x.